We have looked at media access control protocols in the context of bus and star topology, basically the random access protocols. The media access control in ring is slightly different. So in this video, we will see how media access control is done in a ring topology. So many obsoletes in this page. What can be said? The ring could never compete with Ethernet. That is why you see that many of these ring-based technologies have become obsolete. Sometime in mid-1980s, IBM proposed the token ring technology. This goes by IEEE 802.5 by the time Ethernet was already established. So this ring topology was proposed at 4 Mbps and 16 Mbps rates. And since Ethernet was well established by them, this could not compete with Ethernet and it kind of became obsolete. So in 1990s, early 1990s, FDTI said, okay, token ring rates are so small, that is why it couldn't compete with Ethernet. Let me provide 100 Mbps, which is 10 times more than what the current Ethernet then was providing, and thereby I will succeed. It so happened that Ethernet also caught up. So Ethernet then proposed fast Ethernet at 100 Mbps. So this also could withstand the fast Ethernet standard. Thereby this also became obsolete. These two technologies were proposed in the context of local area networks. So resilient packet ring RPR is another technology. It goes by 802.17 standard. This was proposed in the metropolitan area network context, the MAN context. Even here there is a metro Ethernet that is in competition with it, but so far it's not clear whether this can withstand the metro Ethernet competition. We'll see, time will tell. So in this video, we will study the token ring technology just because it's quite simple. I must be wondering, why is this instructor making us study all these obsolete technologies? Well, history is golden and history tends to repeat itself. So the token ring design is a rather an interesting design and there are some lessons to be learned from that. So we will look at token ring just because it's the simpler of the other ring designs, and I'll keep it at a very high level. So going on, as I mentioned earlier, the token ring was conceived by IBM, goes with this particular standard name. It's obsolete because of high cost. It couldn't compete with Ethernet, which was already well established. It has complex management, as we will see shortly, and the equipment that it used was also rather fragile. Well, this is no surprise. Token ring has to work on a ring topology. So this is how the hosts are connected, and data is going to flow in a specific direction at any given time. And the cable that is used is based on twisted pair technology, and token ring, the 802.5 standard, supports 4 and 16 Mbps. And just like in Ethernet, this also has a limit on number of hosts that can attach to a ring. In this case, it is 250 hosts. There is one specific problem with ring topologies, and we have covered it before. What is it? That's right. If one of these hosts were to fail, you don't want the entire operation of the network to fail. So to address that, this is how the rings are configured. So basically they employ this device called MSAU. This stands for multi-station access unit. And many of these MSAUs are interconnected. So this is how the hosts in turn are connected to this MSAU. This is the connector that is used. This plugs into this MSAU in one end and plugs into the host at the other end. So when you interconnect the host to an MSAU, this is internally how the wiring is. So the data that comes from outside, so this in turn may be connected through another AMSAU. So the data from here comes, it goes like this through the host, 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 back to another MSAU. So this is how the MSAUs are interconnected to form a ring topology. Now the question is, what if this host crashed? This is where these relays come into play. Whenever this host crashes, this relay is going to close, thereby establishing a direct connection like this. In this case, the data is going to propagate like this, the packets, thereby bypassing this crashed host. Now that we have seen the topology, let's look at the media access control. But first, which type of media access control does token ring employ? That's right, taking turns protocol. So here is the basic idea. A token is nothing but a 24-bit pattern that rotates around the ring. So a host that is connected to the ring reads in the bits on the link and puts them out on the link. In between, it may buffer a few bits. This buffer is needed because the bits have to be either on the link propagating, or if the length of the ring is not enough to accommodate all the bits have to be buffered in the host. Any sender that has a packet to send, what it does is it captures the token. So once it receives the token, it kind of drains it out, and then it is going to put back whatever frame or packet it wants to transmit onto the link. As this frame circulates around the ring, nodes that are not the receivers are just going to receive the bits and put back the bits onto the ring again. But if the node is a receiver, it is now going to copy this packet. So you are receiving the bits, you are putting them back on the ring, but at the same time you are also making a copy of the bits because you are the receiver for this particular frame. A point to note here is the receiver does not remove or drain the packet from the ring. It is the responsibility of the sender itself. What do you think is a possible reason for this? So if the receiver crashed or is not active, someone has to drain this packet out of the ring. Since the sender put the packet, it might as well drain the packet. There is another reason why this doesn't happen. I will cover that shortly. Once a sender grabbed a token and transmitted its packet, after that it needs to release the token back into the ring, and there are two ways of releasing the token. One is called delayed release, another is called early release. In delayed release, the release of the token happens once the first bit of packet comes back. What do I mean by this? So here is the host. Let me draw here again. And it has now sent a frame out after capturing the token. Now this frame is going to go around the ring, and then the first bit will reach the host again. Now after this first bit has reached, this host is ready to release the token back into the ring. So this is delayed release. In early release, what happens is as soon as the host finished transmission of the frame, so it is kind of transmitting the frame, as soon as it finishes transmission of the frame, it is going to release the token right after. So that is kind of captured here. So here only after the frame, first bit of the frame comes back, the token is released. Here as soon as the transmission of the frame is done, the token is released. So between delayed and early release, which do you think results in better channel utilization or efficiency? That's right, early release does better, because in delayed release, from the time you sent the frame till the time you get back the first bit of the frame, let's say this kind of ended, then you are wasting this resource. Only here you are going to release the token, and thereby someone else can start using it. So in summary, a token passes around the ring. A sender who has a frame to send grabs the token and sends the frame, and after that he is going to release the token based on either delayed release or early release, and then some other sender can capture the token and the process repeats. So the host gets service in a round robin fashion. An interesting question here is, once you grab a token, for how long can you hold it? This translates into how much data you can send before you release the token. The amount of time you are permitted to hold a token is called token holding time. This is a configurable parameter as part of the ring. So if you set your token holding time to infinity, this basically means that you can empty your queue. In other words, keep transmitting all the packets that are in the queue. Once the queue becomes empty, then you release the token. What can potentially be a problem with this approach if you set THT equal to infinity? It's not particularly fair. A few nodes can monopolize the channel. Not only that, if there is some node which has a very small message to send, the delay that is involved in sending the message can become very large, because it now has to wait for all these nodes whose queues are large for them to transmit before it will get an opportunity to transmit. So typically the THT is set to a reasonable value, one or few packets. In other words, whenever a sender grabs the token, it can send a few packets before it is forced to release the token back. So here is the token ring frame format, the frame header format. So the frame header has multiple fields. The start delimiter is that sentinel that is part of many link layer protocols. This is followed by access control. This specifies access information. I will cover this aspect shortly, but the point to note is there are 8 bits as part of access control. These in turn are divided into this, where priority 3 bits, token 1 bit, monitor 1 bit, and reservation 3 bits. The use of these fields I'm going to cover shortly. Following access control is frame control. Basically, this field distinguishes whether the body is carrying some regular data or some control information. This control information is used for managing the operation of the ring. Again, I'll cover this shortly. Just like Ethernet, after frame control is destination address 48 bits followed by source address another 48 bits. After this is the payload, the body, basically higher layer data, and this is followed by checksum, which is again like Ethernet, a 32-bit checksum. And then you have the end delimiter, this is the end flag, and after this is something called frame status, which is again represented by 8 bits, where AC00, AC00. This is what is inside. What are A and C bits? I will cover shortly. Unlike Ethernet, token ring provides a rich set of services, one of which is priority-based service. Normally in networks, certain packets have higher priority than others. For example, real-time application packets, video or audio. Why higher priority? Because these packets cannot really wait for longer times because they have delay constraints. So typically what this boils down to is that you want to send certain high priority packets before you send certain low priority packets. So this priority scheme is supported in token ring, and this is handled through 3-bit priority field as well as a 3-bit reservation bits. These are part of the access control. So here are the priority bits and here are the reservation bits. And this access control is there as part of a frame as well as token. So each packet in this case is assigned a priority based on the application. And whenever a sender has a packet to send, it can seize the token only if its packet's priority is at least as great as the tokens. So this is implying that tokens themselves carry certain priority. But who sets the token priority? This is handled through the reservation bits. So let me give an example. So in this example, there are 5 hosts, host 1, host 2, host 3, host 4, host 5 with different packets with priorities P0, P7, P3, P5 and P2. Now I'm assuming here that P7 corresponds to the highest priority. So what happens here is as a frame circulates around the ring, the hosts are going to set the priority in the reservation bits. So for example, let's say host 1 is sending a frame and it set originally the reservation bits equal to 000. Now as this frame is going round the ring, host 2 will see these bits. It has a packet with priority 7, so it's going to modify these bits to 111. Now as this frame is going, host 3 sees, but it has a priority 3 which is less than the priority 7 that is part of the reservation bits. So it will not alter the reservation bits. Similarly, host 4 as well as host 5 will not alter the reservation bits. Now when this packet is drained by host 1, it is going to release the token. So when this host 1 releases the token, this token's priority is now set to 111, which means that this host 2, because it has a priority at least equal to the token, it is now going to grab the token and it is going to send the frame. Now this frame also has reservation bits which is set equal to 0, and then as these frame goes around the ring, the reservation bits are going to set. Next, when host 2 releases the token, in this particular example, what is the priority of the token going to be? That's right, it will be of priority value 5. So as this frame goes, host 3 will set it equal to 3, basically 0, 1, 1. But host 4 has a higher priority, so it is going to alter these bits and set them equal to 1, 0, 1. This cannot alter it, so again kind of comes back, and then when host 2 releases the token, it is going to set the priority of the token to 5, and this cannot grab because it does not have the required priority, whereas host 4 can grab it because it has the required priority. So what is basically happening is reservations of bits are being set to decide who will transmit next in the next round. Another service that token ring provides is reliability. Remember, Ethernet does not provide any reliability, but here there is a mechanism for the receiver to indicate to the sender whether it received the frame correctly or not. And this is handled through the frame status bits A and C. So this frame status byte is at the end of the frame, and this is how it is, and they are repeated twice here just for redundancy purposes. So whenever a sender sends a frame, originally the A, C bits are set equal to 0, and then whenever a receiver receives this frame, it is going to alter these bits, and A is set to when the receiver sees the frame, and it is C is set to 1 when it copies the frame successfully. And this is how the sender, once the frame comes back, this is how the sender interprets it. If A is still 0, then it knows that the receiver is not functioning or it is absent, in which case it probably takes some action based on that. But if it sees A as 1 and C as 0, it knows that the receiver was present but it could not take the frame, maybe because it did not have enough buffer space. In this case, it will retry later. Now you understand why a frame is removed by the sender and not the receiver, because this will facilitate the reliability as well as priority will be facilitated only when sender removes the particular frame and not the receiver. I have talked about fault tolerance issues in the taking turns protocol. In order to ensure that the ring is operating properly, there is some ring maintenance done. This ring maintenance is done by someone called a monitor. Any host in the ring can actually act as a monitor, but at any given time, only one monitor can be present in the ring. And the role of the monitor is basically to ensure proper operation of the ring. To achieve this role, what the monitor does is it periodically transmits a special control message to show that it is alive. These are typically called keep alive messages, which inform the other nodes that the monitor is alive and active within the particular ring. So this also tells you why frame control is needed, because you need to distinguish between regular data packets and this kind of control packets. So nodes that are part of the ring keep track of this keep alive message. If they do not see such a keep alive message, it's missing for some period, there is an election process to elect a new monitor. So this is how the election process works. Any host that detects a missing monitor will send what is called a claim token frame. This is another control frame. Now it is very much conceivable that more than one host could transmit the claim token frame as part of the ring. Now if this claim token frame sent by a sender comes back to it, then it becomes the monitor. If it didn't come back to it, that means someone else has become the monitor. And this tie is typically broken by the highest address wins. So this example again shows how this works. Suppose host 7 and host 5 both send a claim token. So this is going in this direction. This is kind of coming in this direction. Now host 2, when it sees this, thinks the monitor is H5, but it is going to send that particular frame. So this is also going in this direction. Host 1 thinks H7 is the monitor, and this kind of goes, this is going to go through host 5. Now when it is looking at this particular claim token, it realizes that H7's address is bigger than this, thereby it is now going to set the monitor equal to H7 and it is going to forward that particular frame. Now when it goes through H2, it will alter this and also set it equal to H7. Now this frame of H5, when it goes through H7, H7 knows that its address is better than H5, so it is going to drain the claim token of H5 and not forward it further. So that way H1 always views H7 as the correct monitor. As I mentioned, the role of the monitor is to check the health of the ring. So what can potentially go wrong as part of the token ring? Monitor always ensures a token is always present in the ring. How can a token disappear? Can you think of some ways in which a token can disappear? That's right. A token can be missing because of some bit errors which alter the 24-bit pattern, so you don't know that it is indeed a token. A token can also disappear when a machine crashes. So a sender sent a frame and it had grabbed the token, but before it could release the token, it crashed, in which case there will not be any token present as part of the ring, and no token in the ring means the operation of the ring has come to a standstill. So you need to ensure that the token is always present. So what possible mechanism can the monitor employ to ensure that a token is always present? So a timer can be used for this. So the token typically circulates round the ring, and each host has a token holding time also. So sometime the monitor has to see the token. So it keeps track of when it saw the token last. And now if it did not see the token in some time, which is greater than the time it should see the token, it is now going to create a new one and is going to insert it back in the ring. So how much should you set the value of the timer to be? Express this as a function of the token holding time, and there are n nodes as part of the ring topology, and there is a propagation delay. This is also called the ring latency of D. So the timer is typically set to a value given by what is called token rotation time, the time it takes for a token to go round the ring, and the maximum value this can take is equal to the number of stations multiplied by the token holding time plus the ring latency. There is another role of the monitor, which is to check for orphaned frames. Orphaned frames are those frames where the sender crashed and did not remove the sent frame from the ring. So how would you check for orphaned frames? Basically by using a bit in the header. This bit is called the monitor bit, that is shown indicated here, which is part of the access control. I didn't mention this. The token here is set to 1 if the particular frame is a token frame, otherwise it is set equal to 0. So any sender, when it sends a frame, sets the monitor bit is equal to 0, and the first time the monitor sees the packet, it is going to set it equal to 1, and if it again sees a frame with monitor bit set equal to 1, that means this frame is doing rounds in the ring, the monitor will drain off that particular packet. So in summary, the token ring protocol comes across as more capable than the Ethernet MAC. It is definitely more efficient. There is no randomness as part of the media access control. It supports all these features: priority, reliability, built-in fault tolerance, and so on and so forth. But it's still lost out to Ethernet, mainly because of cost and really complex management. So what is the takeaway? KISS principle. KISS here stands for keep it simple, stupid. So I will leave it for you to read it up on Wikipedia.